So, as a starter question, thinking about what is mechanics, and we've talked about this before in our previous two topics. It's made up mostly of three topics. The first topic we've already done already. The kinematics part of it is a description of motion without thinking about the forces acting. That's our Suvat equations. So we'll be thinking about how fast, how far, how long, etc. So, kinematics, the description of motion without thinking about the forces. We haven't explained anything, but we've described it. If we thought about statics, explaining the forces in the special case of equilibrium, no acceleration, we've done that section as well. So that section was the bit where we looked at force diagrams, free body force diagrams, moments and things like that, and resolving forces. So we looked at how the forces acting on an object balanced out in that special case where it wasn't moving. So the last bit we've got to do is dynamics. We explain the motion in terms of the forces acting, and that's going to be Newton's laws of motion mostly. So that is this topic. So mechanics, studying the motion of objects under a system of forces. We could describe the motion, explain the motion, and there's a special case for equilibrium. So in this topic, Newton's laws of motion is going to be our first lesson where we look at the first and second laws. The next lesson is going to be Newton's third law, inertial mass and some applications of Newton's laws. The third lesson is going to be motion of an object falling through a fluid. That would be terminal velocity. And the fourth lesson is on vehicle safety. Now these things should be a bit of familiarity to you because all of those things were on the GCSE spec. The A-level coverage of them is of course going to go into more detail. We're going to be looking at doing some calculations with things and just a bit more depth. But lots of the things we're on about should be familiar. So when we say lesson 1, Newton's first and second laws, I could ask you, can you already state Newton's laws? The answer, hopefully, should be yes, you can state Newton's laws of motion. I'll ask you that in a sec. I will tell you what the learning objectives are. We're trying to think, here is our spec reference, Newton's laws of motion. You need to know and apply the 3 laws of motion in appropriate situations. Well, that's broad, isn't it? And be able to apply F equals ma for situations where the mass is constant. So how does that slot down for this lesson? We're going to think about what effect a resultant force produces, what would happen to a body already in motion if there was no resultant force. We're going to look at Newton's second law in a variety of situations, but also think about where we cannot apply Newton's second law. So, can we state Newton's laws of motion? Hopefully yes. The first law, objects either stay at rest or move with constant velocity unless they are acted upon by a force. The second law, F equals ma, force is proportional to mass multiplied by acceleration. And the third law, for every force there was an equal force in the opposite direction. You might have heard that stated as, for every action there's an equal and opposite reaction. I don't like phrasing it like that when we write it down. The only reason is because where do we ever hear action and reaction in physics? We normally talk about forces, and it applies to forces. So we're saying wherever there is a force, there is another force equal to it in the opposite direction. As I said, these are on the GCSE spec. You needed to remember them for that. You need to remember them now as well. You need to be able to recall what they are and state them, and you need to know which one is which is first, second, and third. They look straightforward, don't they? But sort of not, because you think if you were riding a bike, you would have to keep pedalling, keep applying that force on the pedals to keep the bike going. But that's not what Newton's first law says, is it? It says, unless it's acted on by a force, it'll stay at constant velocity. So you've got to think in your head, well, what is the other force acting on the bike? When I'm pushing on the pedals, it's the friction, isn't it? There's friction between the bearings on the wheels, friction between the tyres and the road, and friction on the chain as it goes round. So when you're pedalling away at constant velocity, the force of your feet on the pedals is just counteracting the friction. If you wanted to go faster, there would need to be a resultant force. Your pedalling would have to be greater than the friction force. how would that resultant force result in an acceleration? Well, that's what Newton's second law tells us. It tells us that how big the resultant force is, well, that's proportional to how much acceleration you get, how the movement changes. So you can see this is linking into the two things that we've done already in this topic. We looked at in the last bit, Suvat, what the acceleration is. So we could say, if I know the acceleration, I can say how the movement is going to change. If its acceleration is 2 meters per second squared, I know every second it's going to increase in the speed by 2 meters per second. The first bit of that, the force, well, we can calculate resultant forces from our first bit of the topic. We looked at force diagrams, we can compare the forces horizontally and vertically, we can calculate components of forces in those directions too. So, Newton's first law, we'll talk a bit more about that. It is often called the law of inertia. A body will remain at rest or will continue to move with constant velocity unless external forces cause it to do otherwise. You can phrase it like that, or like we did on the previous slide. It remains the same. We're saying that an object either stays still or keeps moving in a straight line at constant velocity unless there is a resultant force acting on it. If the forces are not balanced, the resultant force will cause the object to accelerate. And by accelerate, we mean it can change velocity, direction, or speed. Inertia, that word from the top, is the resistance of an object to being accelerated. So if there is a larger inertia, it's not going to accelerate as fast for the same force. And we should know that that's related to mass. Newton's second law. Resultant force is mass times acceleration, and I've put the units in there as well. Resultant force measured in newtons, mass measured in kilograms, and acceleration in meters per second squared. So if we've got a greater resultant force, the acceleration will be higher. That makes sense. Force and acceleration are proportional. If one is doubled, the other is doubled, and the same is the case for mass. Mass and force are linked as well. So greater mass will require more force to achieve the same acceleration. That's our inertia. Mass, in this equation, is a measure of the inertia of the object, how resistant it is to acceleration. The acceleration is always in the same direction as the resultant force. So if the resultant force is its weight, the force due to gravity, then it's going to accelerate downwards. It's not going to accelerate in a horizontal direction if the only force is gravity. The resultant force, where there is more than one force acting on the object, will be the vector sum of all of the forces acting on it. So we add up all the forces and see which direction the resultant one is, and we can find the resultant force from our topic before last. Sometimes that might involve finding components in the harder questions. So, if we're in class, that would be pretty much it. That's all the input for this lesson. We'd do some experiments. We'd investigate Newton's law. There are 2 experiments that I would get you to do, and we would compare them. There is this one. So this one, if we're looking at the diagram, we've got a ticker timer up on the top right of the diagram, ticker tape leading to the trolley attached with a piece of sellotape. The trolley has got a string coming off the left-hand end going over a pulley to some masses off the edge of the desk. The trolley is travelling down a friction compensating slope. So, we can use a ticker timer and a ramp to investigate Newton's second law. The ramp compensates for friction, which would cause a systematic error. So think about if there were no ramp, then there would be friction between the trolley and the desk. But isn't there already friction anyway, even using the ramp? Well, yes, but we angle the ramp so that the trolley just doesn't move. As in, if you put it a bit higher, it would start to roll down. And what that means is you've compensated for it. It's not that there's no friction, it's just that the angle of the ramp means that it's cancelled out. Why would there be a systematic error otherwise? Well, the mass off the edge of the desk is the accelerating force, but if it's having to work against friction, then the resultant force would be lower. We're going to get an error every time we do the experiment. The ticker tape, coming through the ticker timer, we can calculate acceleration. Basically how the ticker timer works is it puts a dot on the piece of ticker tape 50 times every second. It's at 50 Hertz. And then by the spacing of the dots we can work out how it's accelerating. It's very good. It's a very low-tech bit of kit that we could be able to get some good results with. The experiment would be, if we change the number of slotted masses on the pulley, we can change the accelerating force. Thus, keeping the mass of the trolley constant, we could work out what the acceleration was. So we're proving that accelerating force is proportional to acceleration. We could twist the experiment round and change the masses on the trolley. So instead of changing the masses off the edge of the desk, we could put some extra mass on the trolley and change the mass of the trolley instead and do that bit. The alternative to the ticker timer, we could use light gates to find the time and the acceleration. So we notice there's a piece of card on the trolley, and the piece of card breaks the beam in the light gates. If we know the size of the gap, the software can calculate the acceleration of the trolley as it goes through. Otherwise, it's exactly the same setup. We'd probably have a friction compensating ramp, we'd have the pulley with the masses going off the edge of the desk, and we'd have the trolley. Both of these methods are superior if we just got you standing there with a stopwatch, because of taking out that massive error of your reaction time. That would be a massive random error in the experiment. So it still works in essence the same way. Change the number of masses on the end of the string to see the effect on the acceleration. And that's it. That's the lesson on Newton's first and second laws. So as a plenary question, I want you to think, what is the vector sum? I mentioned that earlier. I said that the resultant force is the vector sum of all of the forces acting on an object. Why would we need to use the vector sum instead of just adding them all up? Well, think about if we had an object that's got two forces acting on it. If one's going right and one's going left, they're going to cancel each other out. So we would need to subtract them. If the two forces were both acting towards the right, we would need to add them together. So it would be the sum instead of the difference. It makes a difference because forces are vectors, so the direction makes a difference.